Physics 2211 Lab 5 on the Slinky drop. So before we go into this presentation, I'll just go over the general contents of this PowerPoint. So firstly, there's the introduction, where I'll discuss the purpose and fundamentals of this lab. Secondly, the procedure, where I'll go over the experimental setup and results. The third, the code, where I'll compare the experimental versus computational models. And fourth, the questions, where I'll answer the what if and what does it mean. So the purpose of this experiment is to analyze the motion of a falling Slinky and determine the impact of its surroundings on its fall. During this experiment, we'll also see how the bottom of the Slinky stays in place when it is dropped. So two of the important fundamentals that we need to know for this experiment are, first off, Newton's second law, which just states that the net force is equal to the change in momentum over the change in time, and in this case, the net force is equal to the force of the Slinky, which is a tension force in the opposite direction of gravity. Adding the gravitational force and the drag force will generate a net force. And then to go more in depth into the drag force, it's in the opposite direction of gravity, and it's equal to the negative velocity squared times the direction of the velocity. So to set up this experiment, first we used Tracker to track the movement of the bottom of the spring in the video. Secondly, we recorded data from the video, including the time during which the bottom of the Slinky remained at rest and the time that it fell. And then we created a computational model of the spring movement using fundamental physics principles and the known times that we just found in the last step. Fourth, we compared the computational model with our tracker model. And fifth, we determined the reasons for difference between the models. So here's just the video of the tracker that we set up. You can see that the bottom of the Slinky just does not move, and then it proceeds to fall down after a couple seconds down, but yeah. So some of the important data that we collected from that video is that, first off, the tracker initial Y position is 0 meters, and it stays at this position from 0.67 seconds to 5.334 seconds. These seconds are just distorted since the video was slowed when we did the frames, so it wasn't really like 5 seconds in between, but it doesn't really matter considering that we used these times also for our computational model as well, so it should have balanced out anyways. The bottom of the string position changes during the interval of 5.334 seconds to 8.335 seconds, and the final Y position is -3 meters. So here are the sections of code that I just used off of reference and then changed off. So the mass we just assumed to be about a quarter of a kilogram, and then we changed to fill in gravity with its natural value, and then we solved for the proportionality constant for the drag force just through plugging in and checking to see our model and how it fit. So before time reached the point where the bottom of the Slinky would fall, essentially the ball velocity was just equal to these settings right here. And then after that, when the bottom of the Slinky was also falling, we had to implement the drag force into the equation. So that's why the FD is different here than the FT. But also there is no FT in this second area because there's no more tension force there. So this is the graph of our experimental versus computational position over time, the blue being the computational model and the orange being the video model. So the reason why you can see that they're pretty similar actually, but there are a few differences. Firstly, it's pretty hard to determine exactly how much drag force acted on the system. Even though we did guess and check with the proportionality constant, it's still probably not perfect fit. Secondly, and what appears pretty important in this table at least, was that the tracker was not placed consistently on the bottom of the spring, we believe, because there's a lot of variation here that's not quite linear, and it should probably be closer to a linear approximation. And then thirdly, the imperfect alignment of the axis that we may have used may have resulted in incorrect displacement values when we were using tracker. So some of the questions I created with for what does it mean, or what if, for the what if question, I asked what if the Slinky was dropped before it was extended out? And the answer to that is there would be no tension force acting on the bottom of the Slinky, and then thus the entire Slinky would fall immediately. Just like how in the previous video there was a period from 0.67 to 5.334 seconds in which the bottom of the Slinky did not drop. That period would just no longer exist in this new scenario. And then for what does it mean, why does the Slinky temporarily remain stationary? And this is because at the bottom of the Slinky, the forces in the Y direction completely cancel out, this being gravity and the Slinky force, which is a tension force. The magnitude of the tension force pulling the Slinky up and the magnitude of the force of gravity are equal and opposite in direction. Thank you.